If I remember correctly, we left off in Precalculus section 3.2 on example 5. So I want to go ahead and pick up this video where we left off. When we graph logarithmic functions, it's actually a lot easier to go ahead and graph the exponential function. So you can just put, you have your base 3 and just put in the values of x as the exponent and calculate the different points. So you have it on your graph. I went ahead and put that one on there. But what I want to do is the math that got us those points. So and then what we do to make it work for logarithmic functions. Okay, so I'm going to make a table of values that we already have graphed here. Since this is f of x, the log is f of x, I'm going to call this g of x. Is the inverse, so base 3 raised to the power of x. And I'm going to go and plot the points, connect them with a curve to give the graph that you see here already. And also show you where and why this table is still useful in order to graph your logarithmic. Okay, so I'm going to have my values of x, and here's my g of x, 3 to the power of x. So I'll start with -2. So 3 to the power of -2 is 1/9. -1, it gives me 3 to the power of -1, that's 1/3. 0, 3 to the power of 0 is 1. 1 is probably about as far as well, that's right, they have different, blah, blah. Okay, 3 to the power of 1 is 3. And I'll go ahead and do 2. 3 to the power of 2 is 9. All right. And so what this does is this gives us our ordered pairs where x is the -2, -1, 0, 1, 2, and y is g of x. It's the 1/9, 1/3. So the reason this is useful for us is because when we are actually plotting f of x, because f of x is the inverse of g of x, that means that its ordered pairs are actually going to be in the form g of x, the y, because inverse, you invert the x and y. So g of x or y becomes your x, and the x values become your y. So when we plug that in, I'm just reversing here. So I'm going to graph the points negative, or 1/9, -2, 1/3, -1, 1, 0, 3, 1, and 9, 2. So these are the points that I can graph in order to get my logarithmic function. Let me make these smaller. All right, so 1/9, -2. -2 goes down 1. This is extremely close to that, the y-axis. And then 1/3 at -1. It's about right here. Here we have our x-intercept. And then at 1, wait, that's 2. Sorry, I have to keep myself straight here. These are in 2s. So that means, hold on, my poor brain. That's -2. So right here, -1, 1/3 is about right here. And at 1, 0, about right here. And then at 3, 1. Let's see here. So that's 1, 2, 3, and then it's about right there. And then 9, 2. So 4, 6, 8, 9, and then up about right here. All right. And so this gives us, mine's never very smooth or on the points, but close-ish. All right. So there is your f of x. That's your log 3 of x, base 3. Okay. So when we graph logarithmic functions, we graph its inverse, the exponential function, and then invert the x and y points in order to graph our logarithmic. It's much easier to calculate. All right. And then I went ahead and gave you all a table that was in the book that kind of breaks down the key properties of an exponential and logarithmic function. So as you can see, this is your exponential function, logarithmic. And so since this is a summary all together, you can see that everything in the exponential and logarithmic functions are inverted. So where the domain of an exponential function is all real numbers, the domain of a logarithmic, or the range of logarithmic function is all real numbers. Where the range of exponential is from 0 to infinity, the domain of logarithmic is from 0 to infinity. Same thing with the asymptotes. The exponential have a horizontal asymptote. The logarithmic have a vertical asymptote. You have the invert of your x and y. What I want to talk about in this slide that I feel like is important is this last little box here, just to make sure. So for the exponential function graphs, they should always contain the point 1b, the base, and -1, 1 over b, right? Because if you have b of x and x is 1, then your answer is always whatever the base is. So the y is always the base. And then if you have b to the -1, it's always 1 over that base. That's where those 2 points come from. And then we see the inverse of that for logarithmic functions. For exponential functions, it's very easy to understand. You raise b to the power of 1 and you get b, like I just showed you. For the logarithmic functions, if x, so in this case, if x equals b, then the function is y equals log b of b, right? X equals b. And then that way we always know that, again, this kind of goes back to, that means our exponent has to be 1 because only any base number to the power of 1 gives us b. So you have to remember that's the answer. Same thing with, if x equals 1 over b, then y equals log 1 over, log of b, 1 over b. That means that y has to equal base raised to the power of -1. So that's why it works with logarithms as well. Excuse me. Okay, so just like with every other parent function that we've ever worked with so far in pre-calculus, you can determine translations based on the way that the function is written. Logarithmic functions, like exponential functions, like rational polynomials, etc. Some facts you need to know, though: when dealing with exponential functions, it is not unusual to have a base between 0 and 1, to have a base that's a fraction. That is extremely unusual with logarithmic functions. You rarely see that in science and mathematics, so we don't really practice it very much with bases that are fractions or decimals. Logarithmic function graphs, like the graphs of every other function we've had, are transformed in similar ways, where the a, of course, is the coefficient of the log. It will vertically stretch or compress graph. The h, and it's always being subtracted from x. Oh, you know what? Another thing. So a negative a will always reflect, always forget that, across the x-axis. The h is always a horizontal shift to the left or right, and the k is always vertical. So up or down. All right, so let's practice this a little bit. So in example 6, we've got, what is it, 3? We have 3 different, I can't remember on y'all's, I feel like on y'all's I didn't give you the blue graph. So if not, I apologize. But you can draw it on there to kind of give you a little bit of practice. So in this case, you can see that it's inside the parentheses. So this is an h situation. So this is like log base 3 of x minus a -2. And therefore, we see that this one shifts left by a factor of 2. All right, so it's a shift of 2 happening to the parent function. You can see also that the asymptote, the vertical asymptote also shifts to x equals -2. And so you will have shifts in the asymptotes and the y-intercepts happening as well. In the next one, in this case, because it's not in parentheses, this one, excuse me, is like a plus k. So this one gives us a vertical shift up to, and you can see that's what we've got here. It's shifted up to. That also means that our x-intercept has shifted. However, because we're not shifting left and right, we still have that vertical asymptote at x equals 0. So there's no change with the asymptote. Let's see her. Okay, last one. We have two things going on here. This one, this is your A. Our A in this case is -2. So this means that we have a reflection on the x-axis, which you can see there in the light blue dotted line. It's reflected. Then it's vertically stretched by a factor of 2. And we can see that as well. Obviously, the x-intercept is not changed, but every point that it has been stretched to, excuse me, stretched by a factor of 2. All right, last little bit is we have more of a application of logarithmic measures. There are a couple of areas that that logarithm is used. Again, logarithm is used to take extremely large numbers and put them on a scale that is much more manageable. And so what that means is that small changes in the scale can have huge impacts in the actual magnitude of whatever it is that's happening. We use this with decibels, so sound intensity. We use this with pH, so acidity and baseness of a substance. And then the example we're going to see here in class today is we use this with the Richter scale, so the amplitude of earthquakes. Now notice in the function that we use, so R equals log of the amplitude over the reference amplitude is a base. It's a common, we're using common log here. See how there's no base. So this means that it's common log. So it's an understood base of 10. And so what that means is that every time we increase anything on our scale, it's actually increasing by a power of 10. So if something is 1,000, it becomes 10,000 or it becomes 100,000. So like you see, you get very large increases with very small changes in the scale. All right, so the question is, what does an earthquake measure on the Richter scale if its amplitude is 10,000 times the small reference amplitude? So there's a nice, easy way that we can take care of this. Because what we can do is we're asked to find 10,000 times the small reference. So this is like 10,000, hold on, let me put it this way. So the A that I'm asked to find is equal to 10,000 times the reference amplitude. So I can take my function R equals log, and instead of A, well, I'll go ahead and write it out. It's A over the amplitude I'm asked to find over the reference amplitude. I'm going to rewrite A as 10,000 times the reference amplitude over the reference amplitude. And you can see that those are in fact going to cancel. And so what this gives me is log 10,000. Now, again, remember, this is the common log. So it doesn't have a base, which means its base is an understood 10. So I can write this as log of 10,000 is equal to the log of, that's 10 to the power of 4. And so that means that my my amplitude or my Richter scale for a magnitude of 10,000 more than the sample is 4. So if we think about this though, let's see here. A Richter scale, I can't remember how to ICH. Magnitude of 4.0 wouldn't even be felt by most people, despite being 10,000 times more than the reference amplitude. So most people wouldn't even feel it. Some would if they're a bit sensitive, and a lot of people wouldn't even know that it happened until they saw on the news that there had been an earthquake like that. But what I want to finish this up by talking about is by what factor. So one of the greatest earthquakes in the United States since the advent of the Richter scale occurred in 1964 in Alaska on Good Friday. It was on March 27th of that year. The earthquake and the resulting tsunamis killed 131 people. And this one measured at a 9.2 on the Richter scale. So what we want to do is see what factor was the small kind of sample that we use, A0, magnified for this earthquake, which measured at a 9.2. So in this case, we know the Richter scale. So that means that the R equals 9.2. So we have log of the amplitude over A of 0 equals 9.2. Now we can switch it to exponential form. By switching it to exponential form, we have our base to the power of 9.2 is equal to the amplitude over the reference. So to solve for A, all we do is we multiply both sides times that reference amplitude. And so we get A equals 10 to the power of 9.2 times A 0, our sample. So this is 10 to the power of 9.2 is the increase of that amplitude, which is enormous. You can plug that into your calculator to see how many zeros you get, but it's a little more than 9 zeros. All right, so what is that? A billion? So it's a billion times greater than the reference is what measures at a 9.2. Some interesting facts when I looked up the any sort of earthquakes over 9.0 worldwide since the year 1500, which they can go back and look at some data, not obviously not numerical data necessarily, but they can look at historical references and see when we might have had earthquakes that hit anything around 9.0. There have only been 5 known earthquakes with a Richter magnitude of at least 9, and all of them have occurred since 1950. Also, all of them happened in different regions of the world. Now, obviously, seismographs weren't around before the 20th century, but there is scientific evidence based on that we can look at from those earthquakes. None of them came close to a 9.0. So they've all been in the last, 75 years now? All right, that's all that I have for this one. I will make a second video that covers the homework that we're going to be working on so that you can try to do it on your own as much as you can, but use it to test your answers, since the next time we meet, most likely we will be having the quiz on 3.1 and 3.2. All right, thanks for your time, guys. I'll see you later.